Well, somebody napped.
Okay, so we are on page 10 of our notes.
Are we?
It's one of the songs that I really
Okay, so when we left off, Max Planck and Victor DeBroglie had basically shown that waves can be like particles, and particles can be like waves. In other words, things aren't separate like we believe them to be under Newtonian or classical mechanics. Remember, under Newtonian mechanics, you're a particle or you're a wave, one or the other. But after Planck and de Broglie, it began to seem that a wave can be like a particle, like light photon, or a particle can be like a wave, like an electron in the single slit and the double slit experiment. Yep, Jordan. Yes, take the red pass. Do not knock into the tripod. So, if particles and waves are supposed to be separate under classical, but we are really beginning to find out they really aren't, that in fact they are just different forms of each other. If particles can act like waves and waves can act like particles, then that would insinuate that matter and energy can also be interchangeable. And that's where, Ms. Sarbacher, we get Einstein's famous equation. E equals mc squared. Einstein, when he wrote his famous paper, he cited nobody in his footnotes, which is kind of a pretty arrogant thing. I know everybody loves Einstein, but the guy was actually kind of a arrogant, creepy dude. When you write your English paper, what do your English teachers say? Cite your sources. Okay? Einstein cited nobody. Why? Because basically he's trying to say, I thought of all this by myself, so I don't need to cite anything. No, not really, because he used Lorentz's mathematics, the Lorentz transformations in his work. He also, you know, built on stuff that Max Planck had already studied, so kind of, I think, kind of arrogant. The other thing that was kind of weird about Einstein, and I can't remember which one went first, but he married his cousin.
What?
But then he cheated on his wife with his double cousin, and then divorced the one and then married the other one.
Wait, how do you have a double cousin?
I can't remember if it was the double cousin first and then the cousin, or the cousin.
Did he have any kids?
Yes, he did have some kids. A double
I have
cousin.
double cousins.
Okay, a double cousin is where your father's brother marries your mother's sister, and then has children.
Oh,
That is disgusting.
No, that's
That's
not
not
disgusting.
weird.
That's,
No.
but dating the cousin
Just
is
be
a little
like,
weird.
wait, your father's
Wait, that's
brother
kind of
married
cute.
or something like
Your
that.
father's
So your
brother
uncle-
marries your mother's sister.
Yeah.
So they're not blood related.
Oh, so your uncle married.
Oh wait, I was thinking
Yeah. Normally your aunt or your uncle, you're only blood related to one of them.
I have
Like
a question.
your
It's like your, you know, one's like
Okay, I
my
was-
dad's
Right.
sister is my mom's brother's wife. Like your mom's.
I have a question, kind of, sort of related.
Okay, go ahead.
If two male twins marry two female twins and they have kids, but like separately, will their kids look this like similar?
No. Oh,
Even though
similar?
they're, like,
Similar,
identical
yes.
twins?
Of course they'll be similar, but they won't be identical. But that's no different than you and your
Does
sister
that make sense?
are similar because you're
No,
coming
but like
from
they're two
parents.
separate, like.
Like the one.
Well, it's no. They will be more similar than you and your cousin.
So it would be like they were.
But there's still gonna be differences
Yeah. So they
because Because if you know anything about probability, there's technically 64 million different combinations between egg and sperm. All right, so Einstein's equation, E is energy in joules, M is mass in kilograms, and C is the speed of light. So let's do an example problem here. What do you say we convert some mass into energy?
Yeah.
And the way you do this, Alicia, is you put the mass into some sort of nuclear reaction. In a nuclear bomb, nuclear reactor. So let's do it. Let's put Mark into a nuclear reactor and change his mass and energy. Thank you, Mark. Mark's mass is approximately 75 kilograms.
How to?
Way to take one for the team, Mark. 75 kilograms. So we plug that in. 75 kilograms times the speed of light times 10 to the 8th meters per second. And then we square it. Put that into our calculator. And I get 6.8 times 10 to the 18th. Now, the units on this should be joules. Now, how do I get joules from this? Well, 1 joule is equal to a kilogram times a meter squared over a second squared. That is a helpful unit to remember, because look what's going on here. Kilograms times meters per second, but it's squared. So it's meters squared over seconds squared times kilogram. That equals a joule. That technically is the definition of a joule. Is a kilogram meter squared over second squared. Now, is this a lot of energy? Let's try to put it into some context. How long could we run a 100-watt light bulb on Mark? So 100 watts, well, what is watt? 1 watt means that you use 1 joule every second. So if it's 100 watts, that would mean how many joules per second? 100 joules per second. On the back of all your appliances, they give the wattage, okay? So that you know how much energy they're using per second. Of course, we want machines that have low wattages, because then they use less energy per second. So, we have this many joules. 6.8 times 10 to the 18. 100 watts means 100 joules are used every second. And then there are 3.16 times 10 to the 7th seconds in a year.
Wait, what's it on top? Oh, 1 year.
1 second. The next 1 year.
Why do you go to years?
Just so that we can go have a little bit more something that we can like maybe turn into a manageable number for our brains to comprehend. The answer is 2.1 times 10 to the 9th years. In other words, just from the mass in Mark, we could run a 100-watt light bulb for 2.1 billion years.
Oh wow.
That's pretty good. Nice job, Mark. But of course, you know, we can't put things like Mark into a nuclear reactor. We can only do this thing with atoms. But still, you can create a lot of energy from destroying mass in atoms. Yeah, Mark and then Kim.
If you had an equation, energy equals mass times the speed of light squared, are you able to find the mass based off of the energy and the speed of light?
Yes. So typically we talk about turning mass into energy, but theoretically possible, we can turn energy into mass. And so like if you like watching science fiction shows like Star Trek, they have like machines that can take energy and create mass. And so you go boop, 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 and all of a sudden a hamburger and fries appear because it turned energy into mass. And now you have your hamburger and fries. I forget what they call those machines in Star Trek. Yeah.
I was actually thinking of a different example, light bridges. Somebody else knew.
Or, yes, yeah, you can turn.
The light bridge.
Yep,
Bridge
Lily.
of
Oh no, wait, Kim was next, sorry.
So when you have like the 100 watts and then you have it over the 1 joule in 1 second, how do you know that it's 100 joules?
Because it's a 100-watt light bulb, so it's 100 joules. A 75-watt bulb would be 75 joules per second. 50-watt bulb is 50 joules per second.
Oh, okay.
And that's also the reason why they want to move the country to the high efficiency bulbs, because they have lower wattages, and so they consume a lot less energy. Yeah, Lily.
What kind of material do they use to, for this?
For
Obviously they're not using lead.
usually uranium and plutonium. Any other questions?
Can I have that?
Okay. So, back to the Broglie. We already have this equation for finding the energy of a wave. We just learned another equation for energy, for the energy in a particle, or the energy in some sort of mass object. So if this equals E, and that equals E, and energy is energy, see what we're going to do, don't you?
No.
Pretty cool. Yeah? Oh yeah. HC over lambda equals E equals MC squared. Set them equal to each other. Now let's do some fun algebra. HC over lambda equals MC squared.
You just wrote. Where did you put the E?
They're equal to each other, so E's gone. I set them equal to each other. HC is equal to MC squared lambda. Divide by MC squared. Then I get HC over MC squared equals lambda. One C cancels with one C. So then I end up with H over MC is equal to lambda.
Can you pause for a second?
Sure. So we have our wavelength, we have Planck's constant, we have mass, and we have the speed of light. So we can use this equation to find the wavelength of things like sound, light, no, not sound. We can use this equation, sorry, to find the wavelength or frequency of any type of wave. Sound, light, earthquake, water,
What does V stand for?
velocity. Now, down here, this equation with wavelength has m in it, mass. So here, this is the equation for finding the wavelength of something that has mass, or a particle. So if we're dealing with a light wave, a sound wave, a water wave, that's how we're going to find our wavelength. But now, with the single slit and double slit experiment, we know that the electron can behave like a wave. So if it behaves like a wave, it must mean that you can calculate its wavelength. So how do you calculate the wavelength of an electron? Use this equation. Except electrons don't travel at the speed of light. Only light travels at the speed of light. So we're going to replace c with v, the velocity. And remember, mass must be in kilograms. Velocity must be in meters per second. Any questions so far?
Wait, so you just changed the V to, or the C?
C to a V. They're both speeds. Okay, so let's try another problem. All right. Oh. I'm going to continue to pick on you, Mark, because that way I only make one person upset. So let's calculate Mark's wavelength. So to calculate Mark's wavelength, we're going to need to know his mass, which is about 75 kilograms. His velocity. At top speed, Mark could probably run 13 meters per second. That's if he's sprinting down the hallway. So, we have pretty much everything we need to plug into the equation, except Planck's constant. Now, is there one mark or a mole of marks? Just one mark. So 6.626 times 10 to the negative 34th joules per second per mark. 75 kilograms times 13 meters per second. Calculate its wavelength. .8 times 10 to the negative 37th meter. Wavelength is in meters. So that's your wavelength, Mark.
How do you know when you use like 6.62 or then 3.9?
If you're dealing with one of them, it's 6.626. If you're dealing with a mole of them, 3.99 times 10 to the negative 13.
How do you know?
The problem will tell you, or in this case, we obviously know there's only one mark. I haven't seen another one like him yet.
Why is it different?
Memorize the
The numbers?
Or you have those are going to attach.
The numbers and the equations will be on the test, but what you really can't memorize, or what you won't be on the test is, like, that's the equation you use if you're trying to find the wavelength of light. That's the equation you use if you're trying to find the wavelength of the particle. So that sort of stuff you have to know.
Oh, light was it?
Well, yes, they're finding that now light is, that all matter has got what they call the dual nature, okay? So everything is both wave properties and particle properties.
Then why do they have to have two different equations? Because if they're like the same, wouldn't...
Because this one doesn't take into the account the mass of the particle.
Oh.
This one does. Okay, so Mark's got a wavelength. So what the heck does that really mean? Well, Mark's radius is about 0.5 meters from shoulder to shoulder. And that's his wavelength. So essentially that's Mark's size. That's his wavelength. Which is bigger, his size or his wavelength? The size, right? I'll just put this over here so you the size of Mark. So even though Mark has a wavelength, it's infinitesimally tiny compared to his size. So even though Mark is vibrating right now, and that vibration has a wavelength, we don't see it. Okay, it's not like we look at Mark and he's going like, okay? Because it's so tiny, we don't notice it. Okay? Yeah, Mark.
No, but when you were talking yesterday about the ultrasound, that
Yep.
you had the wavelength has to be smaller than the object in order to see it.
Yep.
So would that
To use the wavelength to measure it.
Wait, oh, to use wavelength to measure it.
Yep.
Yes, never mind then.
That's why technically there's a limit to microscopes.
But would that, because I guess it's not possible to have a wavelength that is larger than the size of the object unless it's extremely dense.
Well, there is a case like that. Let's do another example problem here, but this time we're going to do it for an electron.
Wait, so you're just showing us what his radius is so that we know that it's not, or that it's bigger than the wavelength?
Yeah, so that's way bigger. But what about for an electron? The electron's mass is 9.1 times 10 to the negative 31st kilograms. The electron travels with a velocity close to the speed of light, 2.0 times 10 to the 8th meters per second. Bless you. So if we calculate the wavelength of an electron, so there's the calculation.
So, wavelength will always be meters, it doesn't matter like what the units are, they have the equation probably.
Well, it's always good to write down the units, but when we're using this equation, your wavelength must be in meters. So that's the wavelength of an electron. Now let's compare that to the radius of an electron. The radius of an electron is approximately 1 times 10 to the negative 13th meters.
What's the point of the radius?
The point of the radius is try to hopefully explain the Heisenberg uncertainty principle to you. Which is bigger, the wavelength or the radius? Wavelength, right? To the negative 12th. The wavelength of the electron is bigger than its size. Okay? Here, with Mark's wavelength is much smaller than the size. So the fact that Mark is vibrating doesn't matter. Okay? It looks crystal clear to us. In fact, everything at the macroscopic level, meaning our everyday world, even though the fact that everything's vibrating with wavelengths and frequencies, doesn't matter because they're too tiny to matter. But at the subatomic level, the electron has got a very large wavelength. Its wavelength is bigger than itself. So if you tried to look at an electron, it would look like it would look like a blur. You would not be able to see it clearly. The electron, if you were tiny and you tried to look at it, it would look like a big old blur. And I try to maybe give you a little bit of an analogy here in that here's a tuning fork, and it's not vibrating right now. But if I make it vibrate and you try to look at it, the ends of it appear blurry to you now.
I was like, why does he say
Right? Because you have to hit it off a rubber. If you hit it on a table, you can break the metal. So it does appear a little bit blurry because it's actually having a fairly large vibration.
Show it to the camera.
Hands. Use it to tune things.
Music.
You're not even.
Moving in his
Good point.
They can barely see.
All right.
Wish I were asking.
So we're just gonna stay home and watch all these
Just to see that.
I would.
Just fast forward to the subject.
So therefore,
Wait, no.
with large objects like Mark, it's very easy to determine their position. Okay? Very easy to determine the position. In fact, we would even say its position is exact or determined. So another example here is a baseball. I'm throwing a baseball. I know. And I want to measure both the position and the speed of this baseball. We do it all the time in sports. How do you measure the position and speed of a baseball? You get a radar gun. Whoops. I have no idea. Poor guy. There's my radar gun. He's holding a radar gun. That's how you measure the speed of things, right? That's what police do. Get out the radar gun to measure your speed English as you're going down Highway PD. Then you shoot your radar wave and you measure the deflection off of it. Now, what happens to the speed of the baseball and the momentum of the baseball? Does it change when you measure it? No, right? The baseball is going to keep going straight. Does it change the speed of the baseball? No. Okay. So we can determine the position of a baseball exactly. They use radar for aircraft. We can find the position of an aircraft exactly, or submarines. The uncertainty would be very small. Uncertainty means literally that, not sure. Okay, well, we know where the baseball is, it's right there. Okay, we know where Mark is, he's right there. The uncertainty, pretty small. Yep, Abby.
If someone's like shooting a radar gun, why is it like bad fun to hold them if they're like being exposed to radar waves? Is it not like
Radar waves are weaker than visible light,
Oh, okay.
so it's not bad. What?
Why are there two people like this?
Because one threw the baseball, the other one's measuring it. Now what happens if we try to measure an electron? So there's my electron traveling along. Here's the person with the radar gun. I send out my light wave. But guess what happens when the light wave hits the electron? It changes the direction of the electron. the electron had been traveling on a straight path. But the light wave changed the direction of the electron. And not only its direction, it changed its speed. And the reason why it changes the direction and speed is because an electron has a wave-like nature. And what happens when two waves interact? They interfere. And so when you try to measure the trajectory of a baseball, nothing happens. When you try to measure the trajectory of an electron, you change its position and you change its speed. Okay? That is called the Heisenberg uncertainty principle. You can never be certain of the position of the electron. You can only state its probable location. Okay? Well, we should probably finish this part right here. So, the position of the electron is uncertain, and therefore its uncertainty would be very high. So maybe what I'll do right here is, so this is what I was kind of talking about yesterday when I was saying that with quantum mechanics, one of the strange things about quantum mechanics is that the interaction between the scientist and the outcome. If I want to measure the velocity of a baseball in our everyday world, it doesn't do anything to the baseball. But if I try to measure the velocity and the position of the electron, what happens? I actually change its position and I change its velocity. So by trying to measure something, I actually change the outcome. Okay? To give you a larger everyday example here, Allison, imagine you're driving down PD. The cop takes out his radar gun to measure your speed. And as soon as he measures your speed, it causes your car to speed up. So how the heck can he figure out how fast you were going? Because the radar gun actually made you speed up. And it actually made you switch a lane. So how can you be certain of what your speed and position was? Because by taking out the radar gun, it changed it. It can't. Yep, Mark.
But I would assume then that trying to measure the position of an electron in a moving baseball, it would not have any effect at all in the baseball, but only on the electrons in the baseball. Or in a living object, or an animate object that is moving, trying to measure.
It would
the
only
position.
be in very small objects, like a single electron.
Okay.
So it could affect a single electron in the baseball, but not the baseball as a whole.
So next time I get pulled over, I should be like, sir, have you ever heard of the something theory? And that's why.
I would not suggest that you try to argue your way out of the ticket by the Heisenberg uncertainty principle, stating that you can never truly be sure of position and speed at the same time. Probably just make the
But they
policeman
would get
angry.
so confused.
No,
they
but
wouldn't
then
know
they'd
what
be
to
like,
do.
whoa, this kid's really smart, they must be responsible.
They'd be
I'm
like, I
sure
don't
that's
know.
exactly
So
what
then
they're
they
going to
won't
think.
Or they'd be like, you're a smart bleep, and they're annoying me, and I'm gonna give them a ticket.
That's right. Please don't, this is going to go on to a whole
Or
world.
confusing
Yes,
someone.
Lily.
Like, side note, but do we have this class tomorrow? Because it's the multicultural.
That's
Um,
Multicultural
Friday.
next Friday.
Next Friday.
Am I on the wrong week?
You're on the wrong week. You're a week ahead of your time.
Oh.
No, I think it's wrong.
Okay,
Yeah,
so,
no,
another way to think of the Heisenberg certainty principle, there's many ways to think of it, and you can't know the exact location, but you can find the probable location. So, under classical mechanics, we know where everything is exactly at all times. Where's the stopper? In my hand. But if it was an electron, Where is the electron?
Right.
What's the probability that it's here?
50%.
What's the probability here?
6.
Okay, that's the best we can do under quantum mechanics,
Except what if you dropped it on the ground?
is to assign the probability.
Left.
Isn't there a chance you dropped it on the ground?
You will never actually know which hand it was in.
It was in your right.
What's in that one?
You will never actually know which hand it was in. So the best you can do is assign a probability.
Tell us.
Which side was it in?
I'm not going to tell you because that's what quantum mechanics.
But
That's the best you can do, is find a probability.
Can you just tell us what hand it was?
No, because I want you to get used to that. With quantum mechanics, there aren't certainties. Okay? There aren't certainties, only probabilities. And that's what makes it difficult for people to understand.
are they like the
This is
same
gonna come back.
relative area though? Like when you're calculating where a particle is, are they kind of in the same general?
In the same general area, but there's different probabilities. All right. The equation. We can write the Heisenberg uncertainty principle not just as a statement, but we can also write it as an equation. Delta x times m delta v is
Delta x what?
delta x times m delta v is greater than or less than.
Pretty sure it's less than.
Can't give me answer correct.
Anyone can have best friends. Anyone can have.
Greater than or equal to h over 4
I
pi.
hate Abby Small.
Shh.
Where does pi come in?
Don't ask.
Well,
Comes in
we're
because,
asking.
Strauss, can
I don't know. I'll be honest, I don't. But it's there. Now, we're running out of time, and I want to give you at least a little bit of heads up on your homework. So now we have a lot more equations to use. Okay?
Today's Thursday, so we're
And
gonna keep on.
quantum worksheet number 1. And questions 1, 2, and 3, you already know how to do. Question number 4. You're calculating the energy in a student. So if you're calculating the energy in a student, you're going to be using, guess what? E equals mc squared. Number 5, you're calculating momentum. Now if you go back in your notes, you'll remember that the equation for momentum is P equals mv.
Strauss?
Yep.
So you said that like Einstein was someone who didn't agree with quantum theory, right?
Correct.
Then why is this equation working?
Lacey McKittrick, please come to the main office. Lacey McKittrick to the main office.
Momentum. You're gonna have to go back in your notes. B, we're calculating the wavelength of a particle.
Do 4A and B use the same equation?
No. 4A and B is the example of mark, so go back and look. 6 you can skip.
Yay.
7 and 8, well actually there's no 8. But 7 you know how to do already.
Okay.
And of course, guess what, Miss Juswick? Units, units, units. If you don't get the right answer, units, units,
Units.
units.
Sounds like you're saying something like units.
I love that movie. That's my favorite movie.
I have a great